Yeah.
You have to say five theorem.
You would want to say, like, you would want to say specifically, you would want to say because a linearly independent set is always less than or equal to in length than a spanning set. You would actually want to say that you understood that's a theorem. Even if you don't know, you're not restating the hypotheses, but you're definitely telling me what the conclusion is, right? I mean, I'm not going to give you a prescription on how many words to use. I know some people in here want to use as few words as possible to describe everything, but it's in your best interest to use more words if you want to make sure that I understand you know what's going on.
For the reduction and extension, should we know how to do that?
You know, I mean, so the thing about the reduction and the extension proof, about those proofs, is not that you need to reproduce the proofs, but that the ideas in those proofs, especially in the reduction lemma, is like, there's an important idea in there, which is you start with a list and then you just chop vectors out of it. You go down the list and cut vectors away until what's left over is linearly independent, right? I mean, that's kind of the fact that the linear dependence lemma can be applied over and over again is something that may come up in another context, right? And the same thing with the extension lemma, where the idea is all those questions on 2C where it's like, oh, take this and then extend it to a basis. The same idea is active in every one of those questions, which is, or what I guess that was 2B, right? Where you say, oh, well, you have some vectors, what do I need to add to make a basis, right? Like that idea of taking a set of vectors and gluing some more on to make a basis for the whole space, that idea is important. You don't need to memorize the proof. I don't know if that helps anyway.
There's no problem was, but the one problem was something like a linear list, and then like proving that to exist.
Yep.
I think it's a complex combination of the list versus one plus.
Okay.
Is it enough to just say from like once you prove that that second list is really independent, that by that theorem you can reduce it or extend it to a basis?
So if you're actually trying to show something concrete and specific as a basis, you actually need to work with the set that you've got. You can't like say, oh, well, if I extended it, then I could reduce it, because you actually have to show me what the specific thing is that you reduce. Now, technically, you guys are going to be allowed to use the dimension theorems as well as the extension and reduction theorems, right? And so what the dimensions theorems tell you is that if you have, so we're going to talk about this today, if you have 5 linearly independent vectors in a 5-dimensional vector space, it's automatically a basis. You don't need to check anything else. You don't need to go back and check the span. So the upshot of once we have the idea of dimension is, once you've got a notion of dimension, you only have to check one of the conditions to show something as a basis, either if it's linearly independent or if it's a spanning set. So in a dimension 5, so like in this space with the, these basis extension things that we've talked about. So the one where U is equal to, 3x, 2x2, 7x4, x4, x5. This one, I think, turns out to be the case that you have one set of vectors that look like U1 is 3, 1, 0, 0, 0, and U2 is 0, 0, 7, 1, 0, and U3 is 0, 0, 0, 0, 1. Well, those are linearly independent by construction. I mean, these things, x1, x2, x3, they're linearly independent because if you set this equal to 0, the only way to make this equal to the 0 vector is to choose x1 and x2, x3 equals 0, right? So if you continued this problem and you extended this to a basis for all of F4, say, as soon as you write down like the rest of the vectors that you're missing, here's one example that would work. If this space is 5-dimensional, which it is, you can just say that this is a 5-dimensional space, right? R5 or F5 is 5-dimensional. If you can show that these things are linearly independent, you have to show nothing else. It's a basis. So as soon as you get 5 linearly independent vectors in a 5-dimensional space, that's it. You can't have any more linearly independent vectors than that, okay, right? Or if you really like showing things are in the span, you could do this. The spanning arguments with these are obnoxious, because you have to show you could write down some arbitrary vector and express it as some linear combination of these 5 vectors, but the same thing, then you wouldn't need to show linear independence, right? So what I would probably do, if I was working on a problem like this, is I would show that this collection of vectors was linearly independent in a 5-dimensional space, and so therefore is a basis for the 5-dimensional space. As what? Yeah, but I mean, there's problems like this in 2C too, is the point I'm trying to make here. Yeah, but it's like when you get to an exam, you can use any tool that we've talked about, right? You're not restricted artificially by the chapter that you happen to be in. You can just use this argument of dimension, right? And there's another argument that we talked about at the end of 2B, which says if you have if you have a basis, you can chop it up any way you want. And what you get out the other side is the bones of a direct sum. So like if you took this and you took this, this is one of the proofs you're talking about, right? Is to show that, you can always find, if you have a U, you can always find a W, so that U plus W is a direct sum that adds up to F5. If you start with a basis, you can always do this by just sorting one part of the basis over here and another part of the basis over here. And they have to be linearly independent, because if they weren't, you'd be able to have a vector that was in both spaces at the same time. Linear independence basically tells you that these have to form, the span of these and the span of these have to form a direct sum. And you have the ability to use all that structure on the exam, right? If you can figure out how to use these structure arguments, you should use them. Don't feel like you're stuck in the techniques that we developed at the very beginning of the chapter. Yep. Absolutely, dude. I mean, I'm basically going to pull the exam. No, I'm going to pull the exam out of the sort of things I asked you on the homework. I mean, absolutely, that's the best way to prepare for this, is to go back and look at the old homework questions for sure, because that's the concepts that we talked about. The concepts we talked about here, the concepts that you guys have practiced. So, like, yeah. There's not so much I can do, right? I mean, there's not that many questions I can ask you in the first 2 chapters of a linear algebra class that are doable in an hour. Anything else? Everybody nervous? No?
Like the homework that's due tomorrow.
I have significantly revised that. So I cut a lot of, I'm going to finish up my, the stuff I want to talk about on chapter 2C today, but I cut the last half of those problems out because I want you guys to have enough time to think about. The early questions are all very similar in the way that they work, and the later questions I think take a little bit more doing, and I want to have more time for you guys to look at those. But I definitely want you to have the ability to work with dimension.
So like 2C, you chopped it off at 11.
Yeah.
2C, and that's so everything before 11.
Yep. Yeah, you should. I mean, this is the sort of thing, like the way this class works is I can't possibly talk about everything in the book anyway. There's not enough time for me to do that. So you are basically going to have to be responsible for picking. I mean, I've already indicated this in a couple of places where I can't do every proof. I'd love to, but I can't. There's not enough time. And so there's going to be questions that refer to stuff that I don't talk about at length in here that you're responsible for reading in the book instead. It's kind of the way these higher level math classes work. Otherwise, I would just be spending all my time. I would just be regurgitating the book basically, and there's just not enough time to do that. We wouldn't make any progress. So, anything else? Okay. Okay. So, what we will be doing? So last time. Oh, okay. Actually, so we defined this last time. What does it mean to talk about the dimension of a finite dimensional vector space? It's the very, very last thing we did. You remember? So we proved, I'm going to give you the last thing we proved, right? So we did this big proof. So we proved that, well, I should make sure that I'm actually on camera here. People are going to yell at me. One of you guys yelled at me about this, so now I'm gun shy. Someday I won't have to do this anymore. So what we proved is that if V is finite dimensional, then every basis of V has the same length. It was a silly argument where we said if you had 2 bases, think about one as being linearly independent and the other is a spanning set, so you get an inequality one direction, and then you reversed the roles and said, oh, well, the other one is linearly independent. The first one was a spanning set, so you get the inequality in both directions. So every basis of a finite dimensional vector space has the same length. And that led us to our big definition, which is the dimension of a finite dimensional vector space. Okay. Finite dimensional vector space. Is the length of a basis. And we call it dim V. So if every basis has the same length, I might as well call it dimension. And we didn't have a chance to do any examples, but R3 is three-dimensional. Now, if we're going to have a meaningful notion of dimension, it should definitely be the case that we recover Euclidean dimension in the sense that we already know, because 1 0 0 0 0 0 1 0 0 0 1 is the basis. Right? Three-dimensional vector space because I have three vectors and a basis for it. P4F. What is P4F? Up to degree 4, right? So this is the span of 1 z squared, z to the third, z to the fourth. This set of vectors is linearly independent. It's a spanning set for P, and there's 5 of them. So P4F is a 5-dimensional space. 1 z squared, z to the third, z to the fourth is a basis. So P4F is 5-dimensional. Can a set of 4 vectors span P4? Why not? It's a 5-dimensional space. That means I need 5 vectors to span it, right? Every basis is 5-dimensional or has 5 vectors in it. And that means any span. Remember, what's operating in the background with the size of the basis in these dimension arguments is this idea that n is less than or equal to m, where n is the length of a linearly independent list. And m is the length of a spanning list. So to be a spanning list, you had better be bigger than or equal to the size of a basis, because a basis is both linearly independent and a spanning list. So there's all kinds of quick questions that can be asked about spaces. Is it possible to have 4 linearly independent vectors in R3? No, you can't have 4 linearly independent vectors in R3 because the largest linearly independent set has 3 vectors in it, because that's the size of a basis. You can't go past that, right? So the basis kind of sets the line for the largest linearly independent set and the smallest list, sorry, the largest linearly independent list and the smallest spanning list. Dimension controls that. But there's this geometry going on in the background that dimension is controlling. So we have a couple of theorems that are going to let us use dimension to its full effect. The first one is if V is finite dimensional, and U, this U, I know it's not a proper capital, but is a subspace of V, then the dimension of U is less than or equal to the dimension of V. Now that seems pretty obvious, right? But why should this, does anybody actually see quickly why this should hold? I'm gonna do the argument here, but why does this argument hold? Why should it be the case that the dimension of U is less than or equal to the dimension of V? How do you even get started?
Based off the basis of V,
If-
there's only so many linearly independent vectors.
So you're right that you want to start from the standpoint of a basis, but you shouldn't start from V because you don't know if you start from V that you're going to get a basis for U. So you guys had your hands up too.
Every vector in U is also in V,
Okay.
so V spans U, I guess you could say.
Oh, you got to be careful what you mean about spanning U, but yes, okay. Oh, so that's qualitatively what you're saying is that because everything in here can be written in here, then
There can't be anything in U that can't be written, or that's not in V.
okay. So how do we hook that into the number of vectors in a basis? Yep.
Could you do something with contradiction? Suppose that dimension of U is greater than dimension of V, and then show that one of the bases is like another.
You can, but you don't need contradiction here. You can do this directly. Contradiction, what you're saying works for sure, but I can do this directly, right? So if I'm doing something like this where I have something small and something larger, I almost always start from the smaller object in a proof like this, right? Because you want to make sure that whatever you do works in both sets. So if you start working in V, it's possible that you might like start writing things down that are true in V but aren't true in U. So starting from U is going to give you something that whatever you do in U will also hold in V as well, right? And that's a typical sort of approach to these. So I'm just going to say, well, let's pick we showed there was an earlier theorem that says that if V is finite dimensional, then and U is a subspace, then so is U. U is also finite dimensional. We showed that like sections ago, right? When we introduced the idea of being finite dimensional. So what I'm going to do is I'm going to pick a basis. Well, U is finite dimensional because V is. So pick a basis for you. You're always allowed to do that, right? Every vector space, every finite dimensional vector space has a basis. So pick a basis for you. What do you know about a basis for you? It's finite. Well, U is finite dimensional, but what the basis, got to be a little bit careful what you mean by finite dimensional. What do you mean? That's the way. So what I'm after is not the actual number. We use the number, but not quite yet. So you're right that this is a finite list that goes from U1 to UN, right? There's finite number of vectors, and these are linearly independent, and they span. Okay. Is this set linearly independent if we think about it as living in V instead of living in U? Yeah, right. If you're linearly independent in the subspace, you stay linearly independent in the big space. You're not going to suddenly lose linear independence because you suddenly are considering the larger space, right? If they're linearly independent in the small space, they're linearly independent in the large one. So U1 up to UN is linearly independent in V. So it's a linearly independent set of vectors in V because everything in U is also a vector in V. Where am I going to get another collection of vectors? I mean, this theorem is about comparing dimensions of spaces. And in order to get dimension, I have to have a basis, right? Dimension, I can't do anything with dimension of a vector space without a basis. So I better have a basis for V running around somewhere too, or I can't say anything about dimension, right? I need dimension both for U and for V, which means I need a basis for U and a basis for V. Let V1 up to Vm be a basis. Can you tell me anything about the relationship between the length of U1 to UM and the length of V1 to VM? Why? No? What's linearly independent? Well, no, this is a basis for U, not V. So they can't be the same because U might not be all of V, right?
I would say that with U1 UN does not span V, but U1 VM does span V.
Okay, it might span V. It might span V. You don't know that. This might or might not span V, but you do know this spans V. Why does that span V? because a definition of a basis, right? V1, so V1 up to Vm is a spanning set. So these vectors are linearly independent of V. That's the basis for U. These vectors are a spanning set for V. That's a basis for V. So what can you tell me about M and N? N must be less than or equal to M because the theorem we were just talking about at the top of the class, right? The length of a linearly independent set is always less than or equal to the length of a spanning set. I mean, we're really working that theorem. Right? It hasn't gone away because of the length, linearly independent length of the spanning set theorem. But if this has at most the same number of vectors that this has in it, then the dimension of U, which is equal to the length of the list of its bases, is less than or equal to the dimension of V, which is the length of its bases. Right? Why spend time on this argument? This is like a sort of fundamental type of argument in this section of the book, right? We use two different bases. You notice we use the fact that bases are linearly dependent, and we use that bases are spanning sets, and we still had to invoke this linearly independent spanning set theorem at the bottom, right? So all of this stuff stays active. You can see how the definitions are all like, there's a lot, the definitions, all of the interplay here comes from the definitions. We're constantly using the fact that basis is linearly independent in the spanning set. Yep.
Is there a problem with the argument of just saying that, you know, you want to be you can either extend it
Well, you would have to say like, so you can't actually you wouldn't reduce it. It's linearly independent, so it would be an extension, right? So there is a pathway to this theorem that runs through the extension, right? Because when you extend, this is the thing, when you extend, you have to say, well, you either extended by no vectors or you extended to a finite number of vectors, but that still requires somehow that you, I mean, it's a more awkward argument, but it's the same basic idea. Because this idea is also in the proof of the extension theorem, right? And so, yeah, you could absolutely move that way too, right? The fact that you can extend to a basis means you're only ever going to increase the size of a linearly independent set. Okay. Okay. So the next argument says, and this is one of the most useful ones, right? So the idea is, if I have a finite dimensional space, being the right length means I only have to check one of the conditions for something to be a basis. Given a list of the correct length, either basis condition implies basis. There's two theorems to show here. The first is if you have a linearly independent set of n vectors, then it's a basis. And the other theorem says if you have a spanning list of n vectors, it's also a basis. Two theorems. But the basic idea is having the dimension of a space means that you know precisely what it's going to be to be a basis. Okay. So here's theorem one. If the dimension of V is equal to n, then how does he actually phrase it? Every linearly independent list n every list of vectors in V that is linearly independent, that the right length is a basis for V. So for example, before I prove the theorem, let's look at an example of how it's used. If I wrote down one 1 plus c and z plus z squared, it's not hard to show that that list of polynomials is linearly independent, right? Linearly independent. Some exercise for you there. Since the dimension of P2 of F is equal to 3, it must be a basis. Avoiding having to check spanning is a really nice thing to be able to avoid, is the upshot of this, right? I don't have to show it's a spanning set. I could just show that it's linearly independent. And that's as easy as saying, oh, well, C1 plus C2, 1 plus C plus C3, Z squared is equal to 0. C3 and C1 both have to be 0, which forces C2 to be 0. So it's linearly independent, right? Usually these things come with conditions that are very easy to check. That make sense? It's a list of length 3, it's linearly independent, so it must be a basis for the two-dimensional, degree 2 or less polynomial. This is the way these arguments tend to work. Okay. So how are we going to prove this? Suppose the dimension of V n, let V1 up to Vn be linearly independent list of V1. Okay. Now what? Well, if it's not a basis for V, what can we do with it? We could extend it, right? The extension theorem says that if this is not a basis for V, it can be extended. So if V1 up to Vn can be extended to a basis. Now there's only two choices. Either you throw nothing in because it's already a basis, or you come up with a vector to toss it to the pile, right? Those are the only things that can happen with extension. Either nothing needs to be thrown in, which is called the trivial extension, or you actually find some vector that you can throw into the pile to make the basis bigger, the set bigger to make it a basis, right? So pick some other vector. Suppose you add a non-zero vector to the extension. So consider V1 of Vn and then a W stuck on the end of it, where W is part of the extension. How many vectors are in this list? N plus 1 vectors in this list. How long is a basis for V? How many vectors in a basis for V? Why?
The dimension is n.
Because V was dimension n, right? So since V is dimension n, any basis E is dimension or is length n. What does that mean about this set? If this is n plus 1 vectors long, but any basis is length n, what do we know about this? It's got to be linearly dependent, right? So V1 up to Vn, comma W is linearly dependent. So I can reduce it to a basis for V, right? But what vector am I going to throw away when I do that? I got to throw away, why do I have to throw away W? Because these were already linearly independent, and the way the reduction theorem goes is you go down the list and you look for vectors that were in the span of the previous vectors. That's part of the operation of how we do reduction. Is V1 in the span of V1? Well, is V2 in the span of V1? No, because they were linearly independent. Is V3 in the span of V2 and V1? No, because they're linearly independent. So when you do the reduction, W is the vector you throw away. By reduction, and the linear independence of the V's, we throw away W. So there was no extension that wasn't trivial. So therefore it was a basis to start with.
Why can't we not just conclude that V1 to Vn has n length and done? Why do we have to do all of these extension?
So the idea here is that what we're trying to nail down right now, so we really want to know, that, so what we know right now is every basis has n vectors in it, right? But we don't know that n linearly independent vectors is a basis, and we don't know that n spanning vectors is a basis. We don't know that yet. We know that if we have a basis, we have n vectors. If we have a basis, we have n vectors. What we don't know is that if we have n linearly independent vectors, we have a basis. Because remember, a basis has two parts, right? A basis is linearly independent and a spanning set. And so what we're trying to show right now is that, like, if we have n of them and they're only linearly independent, then they're also a basis. So that we can replace either spanning set or linearly independent with a number of vectors. Like, I have to prove that. This is something that has to be proved. If I have a linearly independent list of the right length, then it's a basis, is what we're showing right now. We have to use the extension and reduction lemmas because we don't actually know anything about linearly independent vectors by themselves. To show that something is a basis, I have to show that it's linearly independent and a spanning set, or that, like, it violates this. I mean, this right here is basically showing that we can always extend it if it wasn't a basis. So reduce it. Do the extension, do the reduction, you get the same set back again. So the original extension was trivial. So it started as a basis. It seems trivial, but we're building the stuff up from bones. We don't know this yet. We don't know that linearly dependent sets of the right length are bases. And so we have to prove that we're allowed to just throw away spanning set. That's why this is sort of a weird proof, is because we're trying to get around this. We don't want to include spanning set in the definition of a basis if we have the right length. So we have to use a length argument. We're trying to show that length is good enough. So we have to use a length-based argument to do it. Okay, so the upshot is that one gets used all the time because many sets are easy to show are linearly independent. So here's a really easy one. This is a quick true false on a quiz or test. 5, 7, 2, 3 is a basis. True or false? Oh. Why? Now, okay, as in many things in this class, if I say true or false, you can't just say true or false. You have to say true or false and also explain to me why it's true or false. So why is this true?
One is not a scalar multiple of the other.
Okay, which means what?
They're independent.
Okay, so the argument is V1 is not equal to some constant times V2. They're not scalar multiples of each other. So since they're not scalar multiples of each other, V1 and V2 is linearly independent. They live in a two-dimensional space. There's two vectors that are linearly independent, therefore they're a basis. Two linearly independent vectors in a two-dimensional space are a basis. If you want some idea of the geometry of what's going on, what we're saying is eventually you just run out of directions to go. If you're in a two-dimensional space, you have two independent directions you can go before there's no directions left, right? I mean, if you're in a plane, you can go this way or that way, but what other direction is there that's already described by the two that you already have? I mean, up. But as soon as you do that, you leave the vector space, right? So once you're sort of maxed out your number of descriptions, there's no other direction to go. Right. So the second half of this theorem is a spanning list of the right length is a basis. And you can imagine that if we use the extension lemma to do it in one direction, we're probably going to use the reduction lemma in the other one. So it's the second, its companion theorem is if the dimension of V is equal to n, then a spanning list vectors in V length n I give you the even dumber version of this argument, which looks like this. Okay, let V1 Vn be a basis. Sorry, the spanning set for V. How long is that list of vectors? N. Now, if it's a spanning list for V, the reduction theorem says I can reduce it to a basis for V. So this has length N. How long is a basis for V? So how many vectors do you throw away if you reduce it? None vectors, right? So therefore it was a basis to begin with. The reduction is trivial. This is actually the stupidest possible version of this argument. Suppose you have a spanning set in V that is of length N. By the reduction theorem, any spanning list can be reduced to a basis. Any spanning list can be reduced to a basis. How many elements are in a basis? Well, n of them, because the space has dimension n. Any basis for V has n vectors. So how many vectors did we throw away? None. So the reduction is trivial. And V1 to Vn is a basis. So I guess what this gets to is your point that this seems kind of trivial. But the idea is that we had to build all this machinery about the reduction and the extension lemmas in order for this to make any sense at all. I mean, we haven't done much here except say, if a reduction was, every spanning set can be reduced to a basis, but if the only way to do it is to keep without changing the length is to do nothing, then it must have been the case that we started with the basis. We didn't change it, so the reduction just gave us the basis we already had. Sorry if that's logically unsatisfying.
Yeah,
But that's the point of the, I mean, so like, somebody pointed out in an earlier class that the reduction and extension limits seem like they kind of trivialize everything we've done up to this point. And they kind of, that's the point of the reduction and extension limits. They do kind of trivialize the structure of the vector space at this point. Finite dimensional spaces have this beautiful property that we have really rigid controls over how small a spanning set can be or how large a linearly independent set can be. And a lot of these arguments leverage that structure. Okay, so just to reiterate, if the dimension of V is equal to n and V1 to Vn is linearly independent, then I can extend it to a basis, but I can't because that would put more vectors in the list. So therefore, V1 to Vn is a basis. On the other hand, if V1 to Vn is a spanning list, I can reduce it to a basis, but there's already n vectors here, and every basis has n vectors in it, so I do nothing to it, and so therefore V1 to Vn is a basis. The idea we're dealing with here is that the dimension of the space basically lets us get rid of either linear independence or spanning set as a condition we need to check. Okay. Yeah, I mean, these are two separate theorems. Yeah. See, it's an or. It is definitely an or condition, right? Like you don't actually need to check both, just one. It'll save you some work. Okay, so the last bit of section 2.c says how you deal. We could do some combinatorics in here for just a second. I'm just kidding. We're not really doing combinatorics. We're just going to write down something that looks like the inclusion exclusion principle just for a minute. Okay, so I'm going to ask you a question. You can tell me what you think the answer is. Suppose, so you guys are going to tell me what this theorem is. That's what you're going to do. You're going to tell me the theorem. I'm going to lay out the pieces. You tell me what the theorem is. They're all you incipient mathematicians out there. Suppose that V is equal to U plus W, direct sum. And the dimension of U is equal to 3, and the dimension of W is equal to 2. What is the dimension of V? Oh, no, 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 no. So yes, that's what's gonna happen actually. But I made a direct sum here, so what is the intersection in this case? It's only the 0 vector, right? So if I've got a 3-dimensional space and a 2-dimensional space, and they only intersect at the 0 vector, what's the size of, and also V is built from both of those pieces stuck together, what's the dimension of the big space? Well, 5. All the people that said 5 are correct. Also, you are correct in the more complicated way. Okay, so the idea is that if you have a direct sum, so why would this be true? Because you could write down a basis for U that had 3 vectors in it, and you could write down a basis for W that had 2 vectors in it. And because it's a direct sum, they're linearly independent from each other. And that means that you get a basis for the whole deal, right? What if the intersection is not trivial? What if you had the sort of situation look like this? Here's one plane. And suppose you had another plane that cut through it like this. So this is, you think of 2 pieces of paper along a line like this, right? So this space is 2-dimensional. This space is 2-dimensional. Together, if I add every vector in these spaces together, I get all of R3. But what on earth is going to go on with the, I mean, how many dimensions is a plane? 2-dimensional. And this plane is 2-dimensional. How many dimensional is the line where they intersect each other? It's a 1-dimensional space where they intersect, right? So we're going to say that if you took the space U and you added it to every vector in the space W, you would get R3. If I took all these vectors and I added up to all those, I get all of R3 back again. How does the dimension count work? The dimension, stole my thunder. Sorry. No, I'm actually impressed that you managed to pull that out. So it turns out to be the case that when the intersection is non-trivial, the way that you keep track of how the dimension count works is, now in this case, if you made a basis for this and a basis for that, they're not going to be linearly independent. They can't be, because you'd have 4 vectors. And 4 vectors in R3 cannot be linearly dependent. So you have to cut it down. How many do you throw away to do that? 1 vector has to be thrown away. So it turns out that the dimension of R3 is equal to the dimension of U plus the dimension of V minus the dimension of the intersection between U and V. Remember, if U is a subspace and V is a subspace, we had that problem everybody got hammered on the homework. It said that intersections of subspaces are subspaces. So this has a meaningful dimension, right? If it intersects non-trivially, then there'll be some subspace here that has a basis. Intersections of subspaces are subspaces. So the big theorem is awesome because the more subspaces you have, the bigger the list gets, the bigger the dimension counts gets, which is what I mean by inclusion, exclusion. But let's just say that the theorem is this. And we'll do the two subspace theorem. Okay, given 2 subspaces in V, if U1 and U2 are subspace, I'm impressed you guys managed to cook up this theorem. See, mathematicians, U1, U2 are subspaces of V. I don't even need to teach this class. You should be teaching me. If U1 and U2 are subspaces of V, then the dimension of U1 plus U2, notice here I'm using sum and not direct sum, is equal to the dimension of U1 plus the dimension of U2 minus the dimension of U1 intersect U2. And that's all it's meaningful because this is still a subspace. In the special case where it's a direct sum, this just disappears. Okay. If it's a direct sum, you just get this. And I'm curious, so okay, what does the inclusion exclusion principle look like for 3 sets? Okay.
From 0 to 7, continue 0 vector. So then the length of the basis of the 0 vector would be long.
Yeah, the 0-dimensional space. So points are 0. So we think in vector math, we think about points as being 0-dimensional spaces. So point is 0 dimensional, line is 1 dimensional, plane is 2 dimensional. It's a meaningful thing to say a 0 dimensional space. In fact, when we say one direct sum U2 if U1 intersect U2 is just a 0 vector, then the dimension of U1 intersect U2, which is the dimension of not the empty set, but the 0 vector. It's important here that there's something in here, right? Is the dimension of the 0 vector, which is a subspace, which is 0. Because there's nothing in the base, there's 0 vectors in a basis for it, so it has dimension 0. What's the dimension of the empty set? What was the degree of the 0 vector? Yeah, question.
Is the set of just the 0 vectors that the only set ever that has the dimension 0?
Yes. Yeah, because vector spaces are set up, so vector spaces must always contain the 0 vector. And if there's anything else in there at all, then there'll be scalar multiples of it will be in there too. So either vector spaces have an infinite number of points inside of them, or they have a single point, which is the 0 vector. Now, for those of you that are going to continue on to higher level versions of this stuff, you can actually do vector, this sort of linear algebra over fields that are finite. So if you guys have seen a finite field anywhere, ZP, like the integers mod P are a field, right? Because you can, everything has it satisfies all the structural properties that you need to do vector linear analysis with, or linear algebra with. So you can do linear algebra over things that aren't the complex numbers or the real numbers, but it's way more algebraic than what we're doing here, right? And it's like a special case. In fact, for those of you that know what a ring is, you don't even need a field. You can throw the fields away and just work rings instead. And then you can do something called module theory to do that, right? So that's a vector space over a ring is called a module. You have no idea what I'm talking about? Don't worry about it. Just know that every time you think you understand what's going on in math, the mathematician's saying, oh no, kick that hypothesis away and make it harder and do more. All right, so this basically covers this. I did not do this argument. It is a dimension-based argument. I really want to spend some time. Is this exam on Wednesday or Thursday? Thursday. So I will do the proof of this argument tomorrow, and then we'll talk about anything that you guys, like questions that you guys have about the homework for this. You should feel free to turn in the 2C homework, not tomorrow, but Wednesday. That's totally okay if you want to do that instead. On Wednesday, we'll talk about the definition, quiz you guys on definitions and stuff. Yeah, don't. In fact, I'll just generally make a blanket statement here. If you guys want to turn this in like anytime up to the actual exam on Thursday, you're welcome to do that. I don't care. I won't hand it off until Thursday. You need more time to do it. Okay. Yeah, the homework due tomorrow. I will blanket take the homework due tomorrow until Thursday morning. Okay. If you need time to do it. Oh, wait, hold on, wait. If you did your homework and I don't have a score written down for it, please come show it to me. Okay? And revision, just hand me. Okay. And I'll get those back tomorrow if I can. Or I will get them back tomorrow. Revision's in. You just want me to look at yours. Yeah. And it's cool if I turn in the revisions. Yep. All right, who else? That's fine. I know. Cool. All right, cool. What's your last name? Who else? Wait, 10. Why do I have you written down as a? Oh my God, I got a 12 written for some reason. All right, whatever. Me. Anybody else looking to score before you? Okay, who else? Bar, got it. It's fine. I just need something recorded so I'm not like panicked that I don't have stuff written down. Well, gotcha. Thank you. Button. All right. Thank you. What's your question? It's not. What's your actual commitment? No, but like what time? Sorry. I did read that. I just didn't have a chance to get back to you. Okay, so you can either probably the easiest thing to do